So let's see. We will have a makeup lecture on Monday, the finals week, and I believe it'll be here. I'll double check. I look to see whether there's any final exams scheduled in this room or not, but I don't think so. Your final paper is due that same day, so you can either bring it here, or if you want, you can email it to me on that day. Okay? Does anybody have any questions at this point relative to the paper? So, as we've discussed, my expectation is that the paper is properly formatted for publication using the appropriate templates, either in LaTeX or in Word. So that's one of your exercises here, proper referencing, all of that. So if you have any questions about that aspect of things, let me know. All right?
I have a question there.
Yeah.
Is there somewhere to download like those, like
There are.
the packages for the LaTeX?
So what you should do is go to the American Physical Society website for the journal Physical Review, any of the physical reviews. And then there is a link there that gives you instruction for authors. And it gives all the instructions as if you were an author of a paper for submission. How does it work? Okay? I'll email everyone that to make sure you have that information. And then if there are any questions. So for example, there is a package called RevTech, which is the physical review LaTeX package. And it has all of your LaTeX. And they're also, they have the ability to submit as a Word document if you prefer that. That's allowed as well. All right. Okay. Very good. All right. So let's see. So last time we talked about subdoppler laser cooling and the mechanism associated with that, which is sometimes called also polarization gradient cooling. They're one and the same. And the effect is due to an interplay between light shifts and optical pumping when the light is fluorescence. Okay? So, as shown here, if I have an atom which I can imagine optical pumping between different magnetic sublevels, and in particular we're looking at a simple model here based on two sublevels in the ground state, then if this atom were in the presence of sigma plus polarized light, sigma plus relative to the quantization axis that we've chosen to define the atom, then the atom will optically pump from spin down to spin up. Okay? And in doing so, there will also be a loss of energy because the spin-up state is light shifted 3 times as much compared to the spin-down state because of the nature of the Clutch-Gordon coefficients. So the process of optical pumping involves, sometimes this is called Raman scattering, and it's an anti-Stokes. It's bluer than the light that came in, therefore energy is lost by the atom. Okay? And vice versa, if the atom were in the presence of sigma minus polarized light, then it will optically pump from spin up to spin down. And again, the Clapeyron coefficients here, the squares of those coefficients, are such that this state is light shifted down 3 times as much as this. So in the process of optical pumping, again, the atom will go to a lower energy. And that energy is made up by the kinetic energy of the atom. And so this is the basic cooling mechanism. And it happens for slow atoms, much slower atoms than the Doppler capture range, because this optical pumping rate is less than the scattering rate by an amount that depends on the saturation parameter. Okay, so that's the characteristic time scale associated with optical pumping, the photon scattering rate. So we can see how this could work, for example, in a optical molasses in which I don't have a uniform polarization. And the most famous and important example of that is so-called Lin-per-Lin optical molasses. So Lin-per-Lin optical molasses is thinking about optical molasses where the polarization of the beams is not the same. In this case, they're perpendicular to one another. And so if I look at the electric field associated with these counter-propagating plane waves, with this choice of phase here is completely arbitrary. As we discussed, the relative phase between the two beams just shifts the whole pattern. So this phase is just chosen for convenience so that we don't have all kinds of other phases. But if you read this the first time, you look, why the hell is it minus I? Where the heck did that come from? It's arbitrary. You put in any phase here, it will just shift this whole pattern around. So this field is such that the amplitude, the total amplitude here is constant, as we would expect. Thinking about cross-polarized beams, you might think, well, they don't interfere with one another, so the total intensity would be uniform because they're cross-polarized. However, the polarization, the local value of the polarization as a function of the distance along this axis is varying, because the relative phase between the x and y, if they're in phase, then I get linear polarization, and if they're 90 degrees out of phase, then I get circular polarization. Okay, I can't do the polarization dance as good as Bill Phillips does it, but we'll try that video next time. What one sees is that as a function of position along the z-axis, the polarization is varying. For this particular choice of phase, at the origin, it's sigma minus, and then it varies. It such goes every eighth of a wavelength. It goes from circular to linear to the other circular to the other linear to the other circular. It kind of has an anti-ferromagnetic order to it. These days we would call it a spinor optical lattice, and we'll talk more about that soon. So this polarization gradient, when the light is detuned to the red of resonance, creates the perfect conspiracy for excellent and efficient laser cooling. And so what's sketched up here is up on top is the intensity of the electromagnetic field, which is a superposition of two standing waves. A standing wave for sigma minus light and a standing wave for sigma plus light. These two fields here. They are phase shifted by a quarter of a wavelength relative to one another. So where the sigma plus has a node, the sigma minus has an antinode every quarter wavelength. That intensity distribution, that distribution of field, creates an optical potential, which is the light shift potential, the dipole force potential that we discussed, which is different. It's a spin-dependent potential. That is to say, if the atom is in spin down, it sees one kind of light shift. If it's spin up, it sees another kind of light shift as a function of position, because depending on the atom's internal state, it responds differently to the different polarizations of light. So what's sketched here is the potential, which goes down by an amount V0 up to a third V0. So the peak to peak is 2/3 of V0, which is expected. That's the difference in these two light shifts. And it varies periodically as a function of space, because the intensity in sigma plus and sigma minus is varying periodically as a function of space. And so what we see here is what is now known as the Sisyphus effect. If the atom, say, started spin down, it would be in this potential, and as it moves, it loses kinetic energy. That kinetic energy is turned into potential energy, and if nothing else happened, it would just fall back. But the process is such that when all of a sudden this atom finds itself a quarter wavelength over, all of a sudden it finds itself in the presence of predominantly sigma plus light, in which case the atom will optically pump to spin from spin down to spin up. And all of a sudden it will be in this potential well. And then it starts climbing this hill. And then all of a sudden it finds itself in a region where it sees predominantly sigma minus light, in which case it optically pumps back to the other spin, again and again and again. So the poor atom is climbing the hill and then gets transported back to the valley, climbs the hill, transported to the valley, and is using up all that kinetic energy climbing hills, constantly being pumped back into the valleys. And that is reminiscent of the myth of Sisyphus and gives us a very efficient cooling mechanism. All right? The actual limits of the Sisyphus cooling, what the minimum temperature is that can be achieved, is not really completely rigorously understood. I don't think it ever has been. It was explored in the mid-90s to the early 2000s in numerics and whatnot. But the bottom line of it is that empirically what one finds, I mean, eventually if you get colder and colder and colder, the light, as the light shift decreases more and more and more and more. Eventually, in some sense, the light shift isn't enough to create a good cooling mechanism, because the 0 point energy of the quantum motion starts to become greater than the depth of the well. Exactly where that happens is not completely understood. But the bottom line of it is that the minimum temperature that you get as you decrease this light shift, like either detuning farther from resonance or turning the intensity farther and farther down, is about 5 to 10 recoils. It's about a microkelvin, say. The recoil temperature is about 100 nanokelvin. This temperature is about a microkelvin, a few microkelvin. So that's pretty darn cold. Already. And it was a huge surprise when it was first observed, and it was one of the reasons that the Nobel Prize was given to the folks who discovered and explained it. Any questions about that? All right. So here we are in history. We're at 1990, something like that. And so there was now, okay, temperatures are really cold and there wanted to be much better mechanisms for measuring this temperature and really understanding what was going on in optical molasses at these very cold temperatures. So, one of the things that was done was to try to develop some kind of in situ method for measuring the temperature without looking, at time of flight and expansion, letting atoms release from the cooling and the trapping, looking at what's going on as the cooling was happening. And one way to do that is to measure atomic motion through the spectrum of scattered light. So if the atoms are moving, well, then the scattered light is going to be phase modulated relative to that motion. And that phase modulation in time is a shift in the frequency. And so measuring that shift is a measure of the motion of the atoms. Okay? So let's just look at this for a moment from a classical description, thinking about the spectrum of the scattered light. So let's look at a situation where I have some plane wave coming in. I have some polarizable particle, like my atom, which can scatter some of that light. So the scattered light here, well, according to dipole radiation theory, if I have an induced dipole, then that induced dipole is oscillating at the frequency of the drive, that's calling this the light or the laser that's coming in, then the induced dipole moment radiates, and it radiates dipole radiation. So we have an whatever the perpendicular component of that dipole is relative to the direction of propagation. It's the acceleration, right, that gives rise to radiation, so it depends on the square of the frequency. So it goes by k squared. In fact, it's exactly that in CGS units. And then there's a plane wave. Not a plane wave, a spherical wave that comes out. So let me call, there's some origin here. This is the position of the dipole. There's some position of the observer that's looking at the scattered light in some direction. Okay? It's the usual radiation picture that one looks at. So this is just the dipole radiation formula. And in this case, if this dipole, induced dipole here is dependent on the polarizability, there's some local amplitude of the field and some local phase of the field at the position of the particle. Okay. And, this is all oscillating. Now I'm allowing this particle to move, so its position, r prime, is not fixed. It's moving. Okay, so now if we go into the far field, if the position of the observation is very far away, then this spherical wave is phase shifted for ks to ks in the direction of the observer. Okay, that's just doing a expansion of that to lowest order. So, putting that all together, the scattered electric field is a squared alpha E0. And then I get an e to the I q dot r prime e to the I ks r prime. No. This is r, pardon me. R is a minus I. Where q is the difference between the scattered wave vector and the incident wave vector. Okay? That's from here. So this is the phase of the oscillator at the position of the charge due to the drive, and this is the phase shift that is seen due to the position relative to the origin. So if it's at the origin, then there is no phase shift. It's just a spherical wave from the origin. If it's moved away from the origin, then there's this amount of phase shift of the field, the radiated field. And the difference between them is Q. Clear? All right, so now we can look at what the spectrum is, or the Fourier transform of this. Let's look at the particular case. Let's suppose we have a free particle. So the position of the atom that's doing the scattering, the function of time, is moving with some velocity t. It's got some initial position r0, and it's moving with that position. I guess before I do that, I should say one thing right away. Notice that for forward scattering, that is to say, if the scattered wave vector is equal to the incident wave vector, then Q is 0. Okay, so forward scattered radiation is never phase shifted. I mean, that's why we always have, in the forward direction, even if we have random scatterers in all directions, the forward scattered field will always be able to add in phase with the incident wave. I mean, this is also the basis of what's sometimes called Doppler-free spectroscopy. We see that in a moment in terms of if we look at the case where the particle is moving, then my scattered field, it's got all this stuff, which in some sense I'll just carry around for the moment just to write it all out. Then we have e to the I q dot r0 and then we have e to the minus I. Q dot V. When the particle is moving. Okay, so this, of course, if Q, let's look at the case, suppose we look at backscattered light. Or it's light scattered in any direction really relative other than the forward scattered light. Let's look at backscattering, in which case the scatter is in the opposite direction of the incident field. So that Q is equal to 2 AL. Then this factor involves the Doppler shift. So, if I have an ensemble of atoms, a gas of atoms, and that gas of atoms is at some thermal temperature, has some distribution of velocities, and I look at the scattered light, say that is backscattered from the incident field. So I'm going to put my detector, you know, at some small angle backwards relative to this. So I put some detector here, and I put it on a spectrometer. And I look at the spectrum, what would I expect to see? Well, what I would expect to see, let me leave that here. Write it over here. What I would expect to see is some, you know, here's the frequency that I put in. I would expect to see some kind of Gaussian distribution of frequencies with a spread here that was related to the temperature because of the Doppler shifts. What was observed when this experiment was done was the following. There was this broad pedestal of scattered light, but in addition, there was a huge peak, a so-called elastic peak, right at the origin. That is, right at the same frequency. So a huge fraction of the light came out exactly at the frequency that it came in. So what the heck was going on? I mean, this spread was consistent with the temperature, so it wasn't that this was the sub-Doppler part. This was the width associated with the sub-Doppler temperature. Well, the experimentalists who were working at the time knew about this kind of effect where you can get strong enhancement of elastic scattering due to what's known as the Lamb-Dicke effect, which I want to talk about now. So, what's the deal? Well, this elastic peak was an indication to the experimentalists that there was localization of the atoms to regions small compared to the wavelength. Let's just say the atoms were bound They were in bound wells. And the binding of atoms in the wells leads to a strong enhancement of elastic scattering over scattering into any other frequencies. So in order to explore that, what was done at the time was to say, look, optical molasses, this experiment that I sketched out for you was done in 3D optical molasses. 3D optical molasses is complicated because you have 3 counterpropagating beams. At the time, they weren't phase stabilized relative to one another. So the whole pattern of the interference pattern is moving around in some jittery way, and it's complicated. So what was done, and to me this is a beautiful example of how physics works. Lin-Perp-Lin, 1D Lin-Perp-Lin optical molasses was created as a simple model to try to get at the essence of what was going on in the more complicated 3D optical molasses. But given the simplicity of this picture, what we say is let's now re-engineer our system so that it actually is described by this model, at least something close to it. I mean, it was in that case a 1/2 to 3/2 atom, so that nuclear spin and hyperfine and all of that stuff. But still, let's look at 1D optical molasses, 1D Lin-Perp-Lin optical molasses, and let's look at the spectrum of the light that is scattered in the process of laser cooling. Laser cooling involves scattering of light. There's this optical pumping going on. Let's look at the spectrum of the light that's coming out of Lin-Perp-Lin optical molasses. All right? So, what do we have? Well, if we have now this 1D optical molasses, what we have is the possibility, this localization was indication of the fact that the atoms are trapped in the optical potential wells. That is to say, the atoms are rolling around. When they're so cold that they're no longer, by the time they've reached the steady state, they're no longer hopping from well to well, but in fact somehow optically pumping within the wells themselves. All right, so what happens if I have a bound particle instead of a free particle? Well, let's call this the z direction. Our motion along the z direction, classically, let's just say it's oscillating with some amplitude. It's got some oscillation frequency as well. Okay, so it's a harmonic motion. So now my r prime, my scattered field over here, got all these same factors out front, which are not particularly interesting or relevant to the discussion at hand, but I'll write them out anyway. And then I have e to the minus I omega LT minus A cosine omega oscillation T. So what's going on? I'm scattering this light off of these atoms. This is not correct, excuse me. I have the Q. So let me write this out again. It's minus Q. I'm looking at the Q. Let's write it out again. Let me be more clear about the experiment. We have 1D in propylene alcohol molasses. We have two beams. We're going to look at the light that's backscattered from one of these beams. So that my Q is equal to 2 KL, or 2 KL in the Z direction, direction of the lattice. Okay? This was the phase shift that we got from the general scattering theory. Plug that in with this, gives me 2 KLA cosine omega LT. Whereas before we had the velocity here, now the particle is oscillating. All right? So here's the picture. We shine light on this atom. The atom is oscillating back and forth, and it phase modulates the light. And by the phase modulation depends on the frequency at which it's oscillating. All right. So let's put that together. The time dependence the scattered light is of the following form. Let me call this factor eta. How should we deal with this? Well, we can deal with this by noting that we can expand. Let's get a better piece of chalk here. This exponential in a Fourier series. You remember this one? It's got some Bessel functions in it. This is equal to n equals minus infinity to infinity. Bessel j, depending on the absolute value of n, as a function of that amplitude eta, e to the I n, the oscillation frequency t. So, if I have phase modulation, and that phase modulation, the phase itself is oscillating as a function of time, then that phase modulated signal has many Fourier components. In fact, it has an infinite number of Fourier components. And the amount of amplitude in the field in that Fourier component depends on the extent of the oscillation relative to the wavelength, right? Because this factor eta here is the amplitude of the oscillation times k is 2 pi over lambda, so this is 4 pi over lambda, the lambda of the laser that is oscillating. So the amplitude of the oscillation relative to the wavelength is an important parameter that tells me something about how much light is scattered into those other frequencies. Now, those of you who work in the lab know something about acoustic optic modulators. This is exactly what it is. You're modulating a membrane, and that membrane oscillates, and then you get sidebands, right? But here, the thing that's modulating phase is the atom itself. Now, how much power or amplitude do you get in these different frequencies? Well, it depends on these Bessel J's. If the eta is small compared to 1, which is to say the extent of the oscillation is small compared to the wavelength, well, then we could do an expansion. Use the expansion for small arguments of the Bessel J's. So, let's remind ourselves what the Bessel functions look like as a function of their argument. The Bessel J0 is 1 at the origin. All the other Bessel functions are 0 at the origin. So the first order one is linear and it does something. The next one is quadratic and does something. This is J1 of eta. This is J2 of eta. In fact, looking this up, the Bessel functions as a function for eta small compared to 1, the Bessel function is eta to the power n, 2 to the n over n factorial minus 1 over n plus 1 factorial to the n plus 2 eta n plus 2 plus higher order terms in the Taylor series expansion. Okay? So, this says that for small eta, J0 is approximately 1 minus eta squared over 2. J1 is approximately eta over 2. And J2 is approximately eta squared over 8. So for example, if eta were 0.1, then this would be approximately 99%. This is 0.05. This is the amplitude, not the power. The power is the square of the amplitude, 10 to the minus 3, etc., etc. So, what we learn from this is that if we have a bound particle, which is, in this case, thought to be bound near the bottom of a potential well, and if the extent of those oscillations is small compared to the wavelength of the light that is being scattered from that particle, well then the light that is scattered goes into different components. We can write this out here, sum over n minus infinity to infinity. So we get some amount of the light is scattered exactly at the same frequency, that is the n equals 0. Some of it is phase shifted by one oscillation frequency, either to the red or to the blue, and some is scattered 2 oscillation frequencies, etc., etc. And the amount of power that is scattered into those different, what are called sidebands, depends on the extent of the oscillation relative to the wavelength. And this parameter eta is known as the Lamb-Dicke parameter. If the Lamb-Dicke parameter is small, well then the vast majority of the light that is scattered elastically, meaning that the light that is scattered has the same frequency that it went in. There will be some amount of radiation in the sidebands, and the amount depends on the Lamb-Dicke parameter. So, what was observed in this experiment, this was an experiment that was Polyessen's PhD thesis in 1992. I think the reference is Jessen et al. Physical Review Letters, 1992, volume 69, page 49. And what was observed was the following. Doing so-called heterodyne spectroscopy, they looked at the light that was scattered out of these, and there's one of these interplane optical glasses. And what was observed was the following. There was a huge spike off the scale of this board at the light at the elastic peak, right at the frequency it came in. And then there are side bands here that look like this. So, this is what's called the blue sideband, and this is what's called the red sideband. So there are a number of very interesting features in the spectrum. The first thing we notice here is that the vast majority of the light is scattered into the elastic peak. And that was the first indication that our picture of molasses was changing. It's not, molasses you think of as a goopy, amorphous substance. Whereas now we're thinking about potential wells and particles trapped and oscillating in those potential wells. So there is elastic scattering. How elastic is it? Well, there's a number of features that we see here. Firstly, we see an asymmetry in the blue versus the red sideband. And we also see that these are extremely resolved. That is to say, the width of these sidebands is much narrower than the oscillation frequency. That is another thing that's what we'll talk about, which is called Lamb-Dicke narrowing.
Close to the natural level?
No, way smaller. In fact, it's what you might expect is that if you were, at first blush, and certainly the thing I would have said, is that that line width is the scattering rate, because that's the natural dissipative time scale associated with the optical pumping. But it's much narrower than that. Maybe we should step back a moment and ask ourselves, firstly, what is the oscillation frequency anyway in this problem? How big is it? So what we have, so the atoms are trapped in the standing wave of the counterpropagating beams. So I kept trying to keep that, but there's not enough board. I hate room 5. Why do I always have to teach room 5? But anyway, c'est la vie. So we have one of these optical potentials for either the spin-up atom or the spin-down atom. Okay? This, I can write this. It has some peak. Let me call this the peak-to-peak depth of the potential, which in the case that we just had is 2/3 the maximum light shift. That's what it was for the, the 1/2 to 3/2 atom. So this potential, as a function of z, is equal to, it has some peak-to-peak height, and I'll put the node at the origin. Okay, so that it has a well at the origin. So that's sine squared kz. Plus a constant if we want it, the overall potential is shifted by some constant. What's the oscillation frequency then? How would I find that? If I wanted to say, what's the approximate, this is not a harmonic oscillator. So what do I mean? Any suggestions?
Taylor expanding the origin?
Sure, we're just going to say we're going to approximate this thing by a harmonic oscillator. Second derivative, or just look at the first, just lowest order expansion. If I write this so near the origin, this is approximately the peak-to-peak depth. Sine of a small argument is its argument, sine squared is the square of that argument. Okay? And this is 1/2 m omega oscillation z squared. So, from this we can solve and find that if I write it as h bar omega oscillation is equal to twice the peak-to-peak height of that potential, h bar kl squared, divided by, divided by h bar squared. Divided by the mass. Okay? So that's my harmonic oscillator. So this then is equal to, if I multiply top and bottom by 2, this is equal to 4 peak-to-peak times the recoil energy associated with that wavelength and that mass atom. The recoil energy, remember, is the kinetic energy associated with the atom, but it gets h bar k of momentum. So that says that the oscillation frequency here is equal to twice the square root of the peak-to-peak depth times the recoil. So if this is going to be harmonic, firstly, it better be the case that the peak-to-peak depth is huge or big enough compared to h bar omega, because otherwise the 0-point energy starts to get where this thing is anharmonic. Okay, so for this harmonic oscillator approximation to make sense, we want the oscillation frequency to be much, much less than the peak-to-peak depth, which is to say the peak-to-peak must be much, much bigger than twice the recoil energy. Okay. So in the experiments that were done when we're thinking about this in laser cooling, this is certainly the case. I mean, this is not true for modern optical lattices. We'll talk about that probably next week, where the atoms are typically in standing waves that are much shallower, such that the atoms are not trapped very deeply, but in fact can tunnel between these potential wells. But in the context of optical molasses, where I'm fairly close to resonance, like 10 line widths or something like that, so that I'm scattering some photons to cool something, then my potential is deep enough that this matters. And typically these oscillation frequencies, you know, in these experiments, you know, they were on the order of, they were pretty big, on the order of, say, 100 kilohertz, maybe 200 kilohertz. Okay. Is that big or not? Maybe you know, maybe you don't. But for in a modern optical lattice, that's not the kind of oscillation frequencies we're typically talking about. All right, so that's how big. This is, say, 100 kilohertz separated. But what about the width of these and the asymmetry? What's going on with this asymmetry? Well, let's take a look at this picture now from a quantum perspective. So here is the atom near the bottom of this well. Okay? There are quantized energy levels. And what's going on in the context of photon scattering? Well, I'm looking at the photon scattering where the atom is, say, on the cycling transition, coming back to the same internal state. Of course, if it goes to a different internal state, it will go to a different potential, and that's more complicated. We're just looking at the light that corresponds to the cycling transition. Now, we're in quasi-steady state. Well, we're in steady state, which means that there's detailed balance. So there's some distribution of populations in these energy levels that depends on a thermal distribution. The atom is scattering photons. In doing so, it absorbs, say it started in this particular n equals 1 vibrational level of the lattice, or of the potential. So it absorbs, goes up to the excited state, and then it comes back down. It can come back down to the level it started at. It might come down and heat up, go up a level, or it might come down and cool down. These three frequencies correspond to the elastic peak, the blue sideband, and the red sideband. The first red sideband. Of course, there's a second blue sideband and a second red sideband, but they're way down in power because those Bessel functions fall off and we can't even see them. At least I don't think they were seen. Okay? Of course, that's true. This red and blue sidebands exist for starting in all states except the ground state, right? Because if I go up with that same amount of light here, there's nowhere for me to go because I'm in the ground state. So that's a clue as to why there might be asymmetry here. So we can look at this problem now, thinking about this from the point of view of population rate equations. So the population in the nth vibrational level here changes the function of time. There's some transition rate due to this absorption emission, the scattering of photons. Which is some balance of stuff leaving that level, going to some other level, and stuff feeding in from the other levels. Okay? We'll come back in a moment. What are these transition rates? Well, we could get these from Fermi's golden rule or from a master equation description. At the end of the day, what we have is there's the scattering rate. That would be the rate associated with absorbing and emitting photon to the same level. But in addition, we have to take into account, that's all about the internal degrees of freedom. We have to take into account the fact that the atom absorbs a momentum, goes up to the excited state, and emits. So there is an additional term in this case, I'm only looking at the z component. Everything separates into the different directions separately. So what is this term? This is the recoil. Right? The atom starts in some initial state, ends in some final state. Q is the difference in the photon momentum associated with how much it absorbed and how much it emitted. If that Q were 0, well then I have to come back to the same state I started in. But if the Q is non-zero, well then I recoil. And I can have some finite overlap with a different vibrational state. All right. Now, let's ask ourselves, what's the area under these curves? Firstly, let's think about that. That's related to the amount of power that's scattered into those different frequencies. So, we have power in the elastic peak. We have power in the first red sideband. We have power in the first blue sideband. And that power is going to be the sum over all the levels that are occupied, the number of atoms, or the fraction of the population that's in that level, times the rate to go back to where it started. That's the, times h bar omega, that's the power. It's the rate at which I'm scattering back to where I started. The rate at which I go to the red sideband is when I go up a level. If I go up a level, then the light that is emitted is one quantum of oscillation redder than what came in. And if I go down a level, and this starts at 0, but this starts at 1. Then I emit something that's bluer, right? Now I can restart this, relabel it, start it at n equals 0 and just increase the index by 1. Okay? That's just a relabel. And moreover, from this expression, we see that this is symmetric because it depends on the square of this matrix element. So this is equal to gamma m to n. So this is equal to less. Okay? Now, if we are in steady state, if this distribution of populations in steady state is a thermal distribution, well then we know what the populations are in those different levels. It's given by the Boltzmann distribution. So, in particular, what do I want to say here? Yeah. So, to the degree that this is a harmonic oscillator, the probability or the fraction that's in the n plus 1 state relative to 1 is the Boltzmann factor, which is the energy level spacing divided by the temperature in Boltzmann units. So, from this, we see this is equal to e to the minus which is times the power in the red side. And so, another way of measuring the temperature, at least the temperature associated with this degree of freedom, meaning I think about the equipartition theorem and 1/2 kT for each, is by just looking at the ratio of these sidebands. And if there is an asymmetry, that tells me that there is much more population in the ground state than the excited states. And this was one of the first indications that laser cooling can be so efficient that it can cool pretty close towards the ground state. It wasn't, you can't get to the ground state. That would be, I mean, you can try to get close through other techniques we'll discuss in a moment. Sisyphus cooling doesn't get you to the ground state, but it gets you, you know, maybe 90% of the population in the ground state in this kind of potential world. Alrighty. So what about the width of these resonances? What's that about? Well, we have that expression here. The width of the resonance is related to the lifetime. Remember, we've talked about before lifetime broadening. So the rate at which the atoms are leaving and going to the red sideband or the blue sideband is related to these transition rates. Let's take a look at that. Well, we have the bare scattering rate, and then we have this factor. Now, I'm going to rewrite the position operator in the following way. I'm going to write it in terms of the ground state with and the raising and lowering operators of the harmonic oscillator. So let me remind you about the quantum simple harmonic oscillator. If I write the position operator, that depends on the raising and lowering operators with a characteristic width. That depends on the mass and the oscillation frequency. This is just rewriting the position operator in terms of A and A dagger, right? And this is the ground state width. Here, the spread of the Gaussian wave packet in the ground state. So we have a parameter here, which is telling us something about the momentum given in the recoil due to the absorption and emission. That's the factor Q. And the width of the wave packet, which is something like, not exactly, but it's kind of related to that classical amplitude that we had of the motion of the atom moving around in this potential well. So I'm going to call this parameter A amount, kind of my quantum Lamb-Dicke parameter. So let's suppose it were the case, again, we'll look at, let's say that Q is, in this case, is the backscattered light we're looking at. That's what this experiment was observing. That QZ is 2 times the laser wave number for backscattered light. So let's suppose that 2KL Z naught is much, much less than 1. That's to say, we're in the so-called Lamb-Dicke regime. So that the wave packet of the ground state is well localized compared to the wavelength of the light. Well, then I can do an expansion of this exponential. So my transition rate here by the way, in principle, this matrix element is exactly calculable. It's a Laguerre polynomial of some kind. I don't remember what it is exactly. It's the matrix elements of the displacement operator in the Fock basis, but let's just look at it in terms of an expansion. This becomes 1 plus I A Z naught, A plus A dagger, plus order eta squared terms, which are small, and M squared. Well, this we can do easily. What we see is that this is equal to the scattering rate times a delta function and M for the first term. Then we have terms that have to do with going up the ladder by 1 and going down the ladder by 1. Those are the red and blue sideband terms. So plus delta M n minus 1 times the square root of n. That's when I take the lowering operator, then I have eta naught. I have this factor of I plus I delta m n plus 1 square root of n plus 1 That's the raising operator acting on this, delta n plus 1 n eta naught plus dot dot dot, all squared. I wrote this out twice, sorry. It's all screwed up. Pardon me. That looks right. Okay, so what do we conclude from this? Well, what we see is that the rate of elastic scattering is the bare scattering rate. But the rate at which I scatter up or down a level is reduced by an amount that depends on the square of the Lamb-Dicke parameter. So the scattering from n to n minus 1, this is the case that gives me a bluer scattered photon than I started with, is equal to n eta naught squared times the scattering rate. And the guy going up 1 is n plus 1 eta naught squared. So, in particular, what we see from this is the following very important fact, which is that the rate of scattering going up or down a level is reduced. It's reduced by an amount that has to do with the square of this small number. So in particular, the rate to, say, go from 1 to 0 is eta naught squared gamma s. And the rate to go from 0 to 1, well, that's going up. That's this guy, is the same thing, which we expect. And if eta naught is small compared to 1, these are much, much, much less than 1. And this effect is what is called Lamb-Dicke narrowing. If I have a particle and it's bound so that its oscillation extent is small compared to the wavelength that's being scattered, then the rate of scattering that's non-elastic is reduced. And it's reduced by an amount that's related to the square of the Lamb-Dicke parameter. What's going on physically? Let's just conclude to try to understand why physically does that make sense. It's all coming from this fact. The fact that to scatter, I have to absorb momentum. And the change in momentum has to be enough to get me from one state to another. Because this off-diagonal matrix element, remember, position is the momentum displacement operator. It changes the momentum of. So what's going on? Well, if I'm in the Lamb-Dicke regime, when the particle is localized, so let's imagine that this is much, much, much less than lambda. That's the Lamb-Dicke regime. I'm localized much more than the wavelength. Really, 2 pi. That's important. Then, what's the spread in momentum? Well, the spread in momentum is on the order of much, much. The spread of momentum is on the order of this, right? That's what I need to say. And that spread of momentum is much, much bigger than h bar k. Let's call this the laser wavelength. So if I'm localized to a region that's small compared to the wavelength, then my spread in momentum is big compared to that h bar k. Well, so now let's look at the wave function. Let's say I started in the ground state, for example. I could do first because it doesn't matter. I have some spread in momentum. This is my initial wave packet. I come in with this photon and this recoil. It's going to displace this ever so small. And that displacement is going to be tiny compared to the width. And now I had to look at what is the overlap of that displaced wave packet with another wave function. Well, what are the other wave functions? They're all orthogonal. The next one up is my, Hermite Gaussian. And this dotted displaced wave packet has almost all of its overlap with the initial state and tiny amount with an orthogonal state. It's not until this recoil is enough that it can get you to the next orthogonal state that you're going to be able to change your your external wave function. And so that is the quantum mechanical picture of what's going on in Lamb-Dicke narrowing, and why we see such narrow wave functions. In fact, this effect, this suppression of recoil, allows us to yet have another method for laser cooling if we can laser cool bound particles rather than free particles. And it is the method that was first developed in ion traps, because in an ion trap you can trap and confine the particle well, and it's what's known as resolved sideband cooling, which we might have a little chance to talk about before the semester ends. All right, we'll call it quits for today. And next week we'll talk about optical, next section we'll talk about